Welcome to the session 7 of Unit 2 in Digital Signal Processing. In the previous session, we have gone through the graphical method of circular convolution, and now we go towards the matrix method of circular convolution. So, uh, uh, why we are going towards matrix method, the reason is whatever the graphical method we have seen in the previous session, that graphical method is somewhat tedious one. Okay, so there's the graphical method is quite tedious uh, because if there are many samples, this graphical method becomes a little bit complicated. So for that purpose, now we are going towards next method, that is the matrix method. So let me go further. So if I'll go further, then I can say that the matrix method is more convenient one as compared with the graphical method. So in the matrix method, uh, we have to repeat one of the sequences. So there are two sequences. One is x of n, other is h of n. So out of those two, any one sequence I can repeat via circular shifting of the samples. And this method is represented as y of m is equal to circular convolution of x of n and h of n. Okay, so h of x of n is my one sequence, h of n is my another sequence. So I have two sequences with me. So this would be my sequence 1, this would be my sequence 2. So these two sequences I have to take its circular convolution and I have to get this as the answer, that is y of m. Okay, so let us go further now. So this is what is the uh, circular convolution using the matrix method. So what we have considered is, we have considered that one of the sequence is repeated via circular shifting of the samples. Okay, that we have considered. So you have to keep one sequence as it is, and you have to circularly shift the another sequence. So let us consider, let us x of 0, I will keep it as it is, and I will shift the um, h of n. Okay, so this is my first column. So you can consider here, you can see here h of 0, h of 1, h of 2. Like this, if I'll go further, so till I get is h of n minus 1, h of n minus 2. So like this, I will get the sequence. So I have to do the circular shifting. Means what I'm going to do, this last sample I will bring here at the first position. Okay, and then this h of 0 will come in the second row, this h of 1 will come in the third row, so h of 2 will come here, so it is h of n minus 3, it will come here, and this h of n minus 2 will come here. Okay, so like this I have to go on shifting all the columns. Okay, so similarly I can go for the third column. So for third column, this h of n minus 2, I can write in first column, first row, sorry, h of n minus 1, I can bring it in the second row, h of 0 will come in the third row, h of n minus 4 will come here, h of n minus 3 will come here. Similarly, you can do the same thing. So we can see here h of n minus 1, h of n minus 2, h of n minus 3, h of n minus 4, h of n minus 5, and so on. So at the end, let us say here I will get h of 2. So that h of 2 will be here. Then you can go on increasing h of 3, h of 4, h of 5, h of 6. Like this, here would be h of n minus 1. Okay, h of n minus 1. After that, there would be h of 0, there would be h of 1. Next, this h of 1, again this h of 1 you can bring it at the first row into the next column. Okay, so h of 2 you can write here, h of 3 you can write here, h of 4, then h of n minus 1 will come here, h of 0 will come here, and so on. Now further, if I'll if I see the first column and the last column, so after that, this h of 0 is at the first row, and this h of 1 is at the second row, then this h of 3, h of 2 is at the third column, and so on. So this h of n minus 1, which is at the second last, it will come at the last. So now the cycle is complete. Okay. Once I got this, once I have circularly shifted this h of n, then I can do the simple matrix multiplication. Okay, so if I do this matrix multiplication, if I do the matrix, let me use another pen. If I do the matrix multiplication of this h of n, circularly shifted h of n, and this x of n, then I will get the uh, y of m, that is the circular conversion of h of x of n and h of n. Okay, so let us go further now. So now we'll see how to calculate this y of m from this circularly shifted h of n and the h of n. So let me clear all the annotations. Let us see now one by one. So if I want to find out y of 0, what I have to do, I have to multiply this h of 0 with x of 0. I have to multiply this h of n minus 1 with x of 1, h of n minus 2 with x of 2, h of 2, second last with the x of n minus 2, and h of 1 with x of n minus 1. So if I multiply it and if I add it, so what I will do is h of 0 into x of 0 plus h of n minus 1 into x of 1 plus h of n minus 2 into x of 2. Like this, I have to come here, h of 1 plus h of 1 into x of n minus 1. So whatever I will get, that is the value for y of 0. Similarly, we can do the same thing uh, for the second y of 1. Let me clear it. So for that purpose, what we will do is now we will multiply h of 1 with x of 0, h of 0 with x of 1, h of n minus 1 with x of 2, h of 3 with x of n minus 2, and h of 2 with x of n minus 1. Once I do all these things, I will get y of n, y of 1. So like this, I will go for each parameter. Let us go for the last one. Let's go for this one now. Y of, let me use another frame. Yeah, this way I will use. Let's go for the y of n minus 1 now. Let me finish this. Okay. So for the last one, this h of n minus 1, I'm going to multiply with x of 0. This h of 2, I'm going to multiply with x of 1. This h of 3, I'm going to multiply with x of 2. Similarly, I will multiply this h of 1 with x of n minus 2 and h of 0 with x of n minus 1. So I have to multiply it and I have to take the summation of all these terms so that I will get y of n minus 1. Okay. So this is what is the simple procedure for calculating the circular convolution using the matrix method. Okay. So let us go further now. So this is the simplest method as compared to the graphical method. So next is the comparison between the linear convolution and the circular convolution. Okay. So let us understand some few points between the linear convolution and the circular convolution. So first is the results of circular convolution and linear convolution are not the same. Okay, so how it is there? Because if you go for the circular convolution, then uh, y of n will contain the same number of samples as that of x of n and h of n. It means that if suppose x of n and h of n have the n number of samples, if x of n and h of n has number of samples equal to capital N, then y of n will also have the same number of samples. But that is not the case in the linear convolution. So what is happening in the linear convolution is, if in linear convolution, if my x of n has the samples n, if h of n has the samples capital M, then the samples of y of n would be L minus L plus capital M minus 1. So these both the samples of y of n are not the same. So obviously the results of circular convolution and the linear convolution is not the same. Okay. So now how to obtain the same result from the linear convolution as well as from the circular convolution. So the remedy is you can add um, if I say, let us see further. Yeah. So for circular convolution, we will make the length of x of n and h of n equal to n by adding the required zeros. Okay. And suppose in circular convolution, suppose this x of n has L samples and h of n has m samples, then I have to convert this L samples into n. And what is n? N is equal to L plus m minus 1. So it has already L samples. So I have to add m minus 1 samples to this x of n. We'll go for h of n. So it has already m number of samples. And if I want to make it, if I want to make this h of n equal to capital N samples, so I have m already. So it remains is Ln minus 1. So I have to add here L minus 1 zeros. So you have to convert if you want to get the same result with the help of circular convolution also. Then what you do is x of n, for x of n you have to add uh, m minus 1 zeros to x of n, and you have to add L minus 1 zeros to h of n. If you add this, then ultimately the length of x of n will become capital N, length of h of n will become capital N. So ultimately whatever the y of n, that is convolution of x of n, h of n is there, its length is also capital N. So I will get the same result from the circular convolution as well as from the linear convolution. The same thing I have just written here, that will make the length of sequences x of n, length of sequences x of n, h of n equal to capital N. Then that's what we're doing here. Yeah, we are making the length of x of n and h of n equal to capital N by padding the required number of zeros. So I am adding here m minus 1 zeros. I am adding here capital L minus 1 zeros. Okay. So yeah. So now the result of circular convolution and linear convolution will be the same. Let's go towards some remaining properties of DFT. So let us consider the first property as time reversal of a sequence. In the time reversal, let us consider x of n and its endpoint DFT as x of k. And if suppose I will time reverse the uh, signal x of n as x of minus n, then its endpoint DFT would be x of minus k, or subset capital N, or you can see it as x of capital minus k. Okay. So let us go further. Let us try to prove it. So what I know is from the definition of DFT, what I can write. I want I'm using this side now. Okay, so DFT of this x of capital N minus N is equal to, what I have is the expression like this: x of k is equal to x of n e raised to minus a 2 pi k n divided by capital N. N runs from 0 to n minus 1. So this is the definition of DFT. This is the definition of DFT, and this is the DFT of what? DFT of x of n. Here, what I want is DFT of x of capital N minus n. So everything will remain same. Just I will replace this x of n with x of capital N minus n. Okay. So let us go further. Let us put some substitution. So this is the substitution which I'm going to put. So let us consider m equal to capital N minus small n. So if I convert it, so I will get here small n is equal to, this n can be sent towards left hand side, this n can be brought on the right hand side. So what I will get is that small n is equal to capital N minus n. So this substitution I can put here. So this n minus m, n minus capital N minus small n will be replaced with m, and this small n will be replaced with capital N minus m. So that will do in the next step. So you can see here that this, just give me 1 second. So this n minus n is replaced by m, and this n is replaced with capital N minus m. So we can split this exponential part. We can split this exponential part now. Then if you split it, what will I get is this, which you can write this e raised to minus j2 pi k capital N small n. So this n and this n will get cancelled. What remains is second e raised to minus j2 pi k minus m capital N. So if you consider this, if you consider this e raised to minus j2 pi k, then e raised to minus j2 pi k is nothing but what is nothing but cos of 2 pi k minus j sine of 2 pi k. So cos of 2 pi k is always 1, sine of 2 pi k is always 0. So this complete will have its value as 1. So you can go further. So this will get cancelled. Now this minus minus become plus. And what is my standard form is this. So in standard form, what I want the minus sign outside. If I want to compare it, if I want to write it in terms of DFT. So I will write here minus and I will write here minus. Okay. I'll just go further. So what I did now is I have written 1 minus here and I have written 1 minus here. So minus 1 becomes plus. So if I compare this now, if I compare this equation with this equation, then what is the difference? Here in this k, here it is k, here it is minus k. So simply I can write it as x of minus k, and how many points of DFT are there? That is capital N. So I can simply write here x of n minus k. So like this, you can get this proof. So now it is proved. So you have started with a DFT of x of n minus n. We have started with this, and we ended with this. So it is proved. So if we circularly fold any sequence, then its DFT will also get circularly folded. Okay, so that is what is the conclusion from this property. Let us go further now. Let's go to the next property. So that is what is the circular time shift of a sequence. Yeah. So let us go further. So what is the statement? The statement is if x of n, its endpoint DFT is x of k, then if I'll sequentially shift the sequence, means I'm going to do this x of n minus l, n indicates the uh, point DFT. So it is equal to what? It is equal to, if I shift the sequence in the time domain, it will get multiplied with the exponential component as e raised to minus j 2 pi k L upon capital N, or otherwise you can say it as W subscript capital N superscript K L. Okay, that's what is the Tudel factor. Okay, so let us try to uh, go further. Let us try to prove it. So from the definition of IDFT, so we know the definition of IDFT in terms of Tudel factor. You can write it that x of n is equal to IDFT of x of k. That is 1 upon a. K runs from 0 to n minus 1 x of k. In terms of Tudel factor, you can write e raised to minus j 2 pi by capital N, and sorry it is minus kn. Okay, so if you solve it further, then e raised to this minus will become plus, so we say 2 pi kn divided by n. Okay, so ultimately we got the IDFT expression here, yeah, which are learned. So let us go further now. So IDFT of this x of k, what I want is this. What I want is this. I have to find out the IDFT of this. Okay. What I know as per the definition is IDFT of this x of k, and I want IDFT of this x of k, w and k, w and k l. So each of these x of k, I'll write this x of k, w and k. Now you can club these two terms. So if I club these two terms, then the minus k I can take it outside. So what remains inside is n minus l. Okay. So if it is n minus l, you can observe here. So this is my uh, basic equation. So it is x of n because here this is n. So if I compare this complete expression with this, everything is same except this n minus l. So ultimately I can write x of n minus l. Okay, you can see here. Okay. So in this way, uh, we can conclude this as shifting in time domain by L samples is equal to multiplying the sequence in frequency domain by e raised to minus j 2 pi k small l upon capital N. Okay, fine. So this is what is the proof for the circular time shifting. Let's go further now. Next property, that is circular frequency shift. So this is also referred as the quadrature modulation theorem. Okay. So this property states that multiplication of x of n, multiplication of x of n by e raised to plus or minus, means you will multiply x of n with any exponential component, phasor components, then it will result into the circular shift in the frequency domain by the corresponding samples. Okay. So the same thing I have just mentioned here. Mathematically, I can write it as x of n. If its endpoint DFT is x of k, then, and if I'll multiply x of k with uh, with this phasor component, with this L, then its endpoint DFT will be equal to the shifted version of L by L samples. So I can write here x of k minus L, and it is n point DFT, capital N. So this is what is the circular frequency shift property. Next comes is a multiplication of two sequences. So what I know is multiplication of two sequences in time domain is equal to the circular convolution in the frequency domain. Okay, so that I can simply write here, if x1 of n its endpoint DFT is x1 of k and x2 of n its endpoint DFT is x2 of k, then if I multiply these two sequences time domain, then I will get a circle. I have to do the circular convolution between their DFTs in the frequency domain. So next is the circular correlation. So we can see here that it is circular correlation between these two sequences. Circular correlation of two sequences in time domain is equal to the multiplication of DFT of one sequence with the complex conjugate of DFT of another sequence. What I can write mathematically is, if again x of n its endpoint DFT is x of k, y of n its endpoint DFT is y of k, then circular convolution, you can indicate the circular convolution like r, x, y, l. Then circular convolution of those two sequences, the circular convolution of x of n with y of n, then its endpoint DFT is equal to r x y of k, and that is equal to what? That is equal to multiplication of one DFT as it is and the complex conjugate of another sequence DFT. So that is what is the correlation theorem. Okay. So let's go further. So next is the complex conjugate property. So the complex conjugate property, what you can say is the DFT of complex conjugate of a signal, DFT of a complex conjugate of a sequence is equal to complex conjugate of DFT of that sequence with the sequence divided by k samples. Yeah. So let us see it mathematically. So if x of n, its endpoint DFT is x of k, and if I need to find out the DFT of complex conjugate of sequence, means I have to find out the DFT of complex conjugate of sequence, means I have to find out the DFT of complex conjugate of x of n, that is x asterisk of n. So it is equal to what? It is equal to complex conjugate of DFT, complex conjugate of DFT with the sequence delayed by k samples in frequency domain. So it would be x asterisk of n, and this n is delayed by k samples. Okay. So that is what these are the properties of DFT which we want to uh, see today. So in the next lecture, probably we'll go towards the linear filtering techniques based on the DFT. So thank you so much for this session.